What if everything you see, touch, and even feel is just the surface of something far deeper and more mysterious? Imagine a hidden layer of reality, invisible to the naked eye, where the very fabric of existence is woven together by something called quantum fields. These fields are not just the foundation of the universe, they are the universe. Every particle, every force, every flicker of light emerges from these invisible, ever-present fields. But what are they really, and how do they shape the cosmos we live in? Today, we're diving into the heart of this mystery with 30 mind-bending theories about the universe's quantum fields. From the Higgs field giving mass to everything around us, to the strange possibility of a multiverse bubbling out of quantum fluctuations, we'll explore the ideas that challenge our understanding of reality itself. By the end of this journey, you'll see the universe in a whole new light, one where the ordinary becomes extraordinary and the impossible starts to feel within reach. So, are you ready to uncover the secrets of quantum fields and the mysteries they hold? Let's begin. Now that we've set the stage for the mysteries of quantum fields, let's take our first step into understanding them. Quantum field theory is the cornerstone of modern physics, and it's where the magic begins. Picture this: instead of particles being tiny, solid dots, they're more like ripples on the surface of an invisible ocean. These ripples are excitations of underlying fields that stretch across the entire universe. Every particle you know, electrons, quarks, even photons of light, are just tiny vibrations in their respective fields. But where did this idea come from? Quantum field theory emerged in the early 20th century as physicists tried to reconcile quantum mechanics with Einstein's theory of relativity. They realized that particles couldn't be understood in isolation. They had to be seen as part of a larger, interconnected system of fields. These fields are always active, even in what we think of as empty space. They fluctuate, interact, and give rise to the forces and particles that make up our reality. Without quantum field theory, we wouldn't have the standard model of particle physics, which explains how the universe works at its most fundamental level. It's not just a theory, it's the language we use to describe the very fabric of existence. So, as we dive deeper into these 30 theories, remember this: quantum fields are the stage and particles are the actors. And the story they tell is nothing short of extraordinary. Now that we've laid the groundwork for quantum field theory, let's take a closer look at how it shapes our understanding of the universe through the standard model of particle physics. Think of the standard model as the ultimate rulebook for how particles and forces interact. At its core, this model is built on the idea that everything in the universe, every particle, every force, is a manifestation of quantum fields. These fields are like invisible threads woven into the fabric of reality, and particles are simply the vibrations or excitations of these threads. Take the Higgs field, for example. This is a special quantum field that gives particles their mass. Without it, particles would zip around at the speed of light, and the universe as we know it wouldn't exist. The Higgs field interacts with other particles, slowing them down and giving them substance. This interaction is what we call the Higgs mechanism, and it's a cornerstone of the standard model. But the Higgs field isn't the only player in this cosmic game. There are other fields too, each responsible for different particles and forces. The electromagnetic field, for instance, gives rise to photons, the particles of light. The strong force, which holds atomic nuclei together, emerges from the gluon field, and the weak force responsible for processes like radioactive decay is tied to the W and Z boson fields. What's truly fascinating is how these fields interact. They don't just sit there, they fluctuate, exchange energy, and create particles in the process. For example, when two electrons repel each other, it's not because they're pushing against each other directly. Instead, they're exchanging photons, which are excitations of the electromagnetic field. This exchange is what we perceive as the electromagnetic force. The Standard Model has been incredibly successful in explaining the behavior of particles and forces, but it's not the final word. There are still mysteries it can't fully explain, like dark matter or gravity. Yet, it remains one of the most powerful tools we have for understanding the universe. It's a testament to how quantum fields underpin everything from the tiniest particles to the vastness of space. As we move forward, keep in mind that the Standard Model is just one piece of the puzzle. It's a framework built on quantum fields, but there's so much more to explore. Next, we'll dive into the Higgs field in even greater detail, uncovering how it shapes the very fabric of reality. Now, let's zoom in on one of the most fascinating players in the quantum field arena, the Higgs field. This field isn't just another piece of the puzzle. It's the reason particles have mass, and without it, the universe as we know it would be entirely different. So, what exactly is the Higgs field and how does it work? Let's break it down. The story of the Higgs field begins with a question that puzzled scientists for decades. Why do particles have mass? In the early 1960s, a group of physicists, including Peter Higgs, proposed a groundbreaking idea. They suggested that an invisible field permeates the entire universe, interacting with particles and giving them mass. This field became known as the Higgs field, and the particle associated with it, the Higgs boson, was finally discovered in 2012 at the Large Hadron Collider. This discovery was a monumental moment in physics, confirming a theory that had been decades in the making. But how does the Higgs field actually give particles mass? Imagine the Higgs field as a kind of cosmic molasses. As particles move through this field, they interact with it, and this interaction slows them down. The more a particle interacts with the Higgs field, the more mass it gains. For example, particles like electrons interact weakly with the field, so they have less mass, while particles like the top quark interact strongly, making them much heavier. Without this interaction, particles would zip around at the speed of light, unable to form the stable structures that make up matter. The implications of the Higgs field go far beyond just giving particles mass. It plays a crucial role in shaping the very fabric of the universe. Without mass, particles wouldn't clump together to form atoms, stars, or galaxies. The Higgs field is essentially the glue that holds the universe together, allowing the complexity and diversity we see around us to exist. It's a cornerstone of the Standard Model, but it also raises new questions. For instance, why does the Higgs field have the specific properties it does? And could there be more fields like it that we haven't discovered yet? As we continue to explore the mysteries of the Higgs field, one thing is clear. It's not just a theoretical curiosity, it's a fundamental part of reality. Its discovery has opened up new avenues for understanding the universe, and it reminds us that even the most invisible forces can have the most profound impacts. Next, we'll take a closer look at another quantum field theory that has revolutionized our understanding of light and matter: quantum electrodynamics. Now, shifting our focus to another cornerstone of quantum field theory, let's dive into the world of quantum electrodynamics, or QED. This theory is the quantum version of electromagnetism, and it's one of the most precise and successful frameworks in all of physics. But what exactly is QED, and why is it so important? Let's unpack this fascinating theory. Quantum electrodynamics describes how light and matter interact at the most fundamental level. It's the theory that explains everything from the glow of a light bulb to the way your phone's screen displays images. At its core, QED is built on the idea that electromagnetic forces are carried by particles called photons, which are the quantum excitations of the electromagnetic field. These photons act as messengers, transmitting the force between charged particles like electrons and protons. One of the most remarkable things about QED is its incredible accuracy. The theory makes predictions that have been tested to an astonishing degree of precision. For example, it predicts the magnetic properties of electrons with such accuracy that the results match experimental measurements to within 1 part in a trillion. This level of precision is like measuring the distance from Earth to the Moon and being off by less than the width of a human hair. It's no wonder that QED is often hailed as one of the most successful theories in the history of science. But how does QED actually work? At its heart, the theory relies on the concept of virtual particles. These are particles that pop in and out of existence for incredibly short periods of time, mediating interactions between charged particles. For instance, when two electrons repel each other, they are actually exchanging virtual photons. This exchange creates the force we observe, even though we can't directly see the photons themselves. It's a strange and counterintuitive idea, but it's been confirmed by countless experiments. QED also provides a framework for understanding phenomena like the emission and absorption of light. When an electron in an atom jumps from a higher energy level to a lower one, it emits a photon, a particle of light. Conversely, when a photon is absorbed by an atom, it can boost an electron to a higher energy level. These processes are at the heart of everything from lasers to the colors we see in a rainbow. The success of QED has had profound implications for physics. It not only deepened our understanding of electromagnetism, but also paved the way for the development of other quantum field theories like quantum chromodynamics, which describes the strong force. QED also played a crucial role in the development of the Standard Model, the overarching framework that describes 3 of the 4 fundamental forces in the universe. As we continue to explore the quantum world, QED stands as a testament to the power of human ingenuity and the beauty of the universe's underlying laws. Its precision and predictive power remind us that even the most abstract theories can have real-world applications, shaping the technology we use every day. Next, we'll turn our attention to another quantum field theory that governs the strong force quantum chromodynamics, or QCD. Now, let's venture into the realm of quantum chromodynamics, or QCD, the theory that governs the strong force, one of the most powerful yet mysterious forces in the universe. While quantum electrodynamics explains how charged particles interact through photons, QCD takes us deeper into the heart of matter, revealing how quarks and gluons come together to form the building blocks of atomic nuclei. At the core of QCD are quarks, the fundamental particles that make up protons and neutrons. But quarks don't exist in isolation. They're always bound together by gluons, the carriers of the strong force. Think of gluons as the glue that holds quarks together, hence their name. Unlike photons in electromagnetism, which don't interact with each other, gluons interact with one another, creating a complex web of forces that make the strong force unique. One of the most fascinating aspects of QCD is something called confinement. This principle states that quarks can never be found alone. They're always confined within particles like protons and neutrons. If you try to pull quarks apart, the force between them actually gets stronger, much like stretching a rubber band. This is why we've never observed a free quark in nature. They're always bound together in groups of 2 or 3. The strong force is also responsible for holding atomic nuclei together. Protons and neutrons, which are made up of quarks, are packed tightly in the nucleus. Despite the repulsive electromagnetic force between positively charged protons, the strong force overpowers it, keeping the nucleus stable. Without QCD, atoms as we know them wouldn't exist, and neither would the matter that makes up our world. Another intriguing feature of QCD is asymptotic freedom. At extremely short distances, such as those inside a proton, quarks behave almost as if they're free particles, experiencing very little force. But as they move farther apart, the force between them grows stronger. This counterintuitive behavior was a groundbreaking discovery and earned the physicists who uncovered it the Nobel Prize. QCD also introduces the concept of color charge, a property of quarks and gluons that's analogous to electric charge in electromagnetism. However, instead of just positive and negative charges, quarks come in 3 colors: red, green, and blue. Gluons, on the other hand, carry a combination of colors, allowing them to mediate the strong force between quarks. It's important to note that these colors aren't literal. They're just a way to describe the different states of quarks and gluons. The implications of QCD extend far beyond the nucleus. It plays a crucial role in understanding the early universe, where quarks and gluons existed in a hot, dense state known as the quark-gluon plasma. By recreating these conditions in particle accelerators, scientists have been able to study the behavior of matter under extreme conditions, shedding light on the origins of the universe. As we continue to explore the quantum world, QCD reminds us of the intricate and beautiful complexity that underlies even the most familiar aspects of reality. From the stability of atoms to the explosive energy of stars, the strong force shapes the universe in profound ways. Next, we'll delve into another fascinating aspect of quantum fields, the vacuum state, and the mysterious concept of zero-point energy. Now, let's shift our focus to a concept that might sound paradoxical at first: the quantum vacuum. Far from being an empty void, the quantum vacuum is a bustling arena of activity where fields are never truly at rest. This is where we encounter the fascinating idea of zero-point energy, a phenomenon that challenges our everyday understanding of emptiness and energy. In classical physics, a vacuum is often thought of as a space completely devoid of matter and energy, but in the quantum world, things are far more dynamic. Even in what we call a vacuum, quantum fields are constantly fluctuating. These fluctuations give rise to what's known as zero-point energy, the lowest possible energy that a quantum system can have. Unlike classical systems, which can reach a state of zero energy, quantum systems always retain this residual energy, even at absolute zero temperature. To visualize this, imagine the vacuum as a calm sea. At first glance, it appears still, but beneath the surface, there's a constant churning of waves and currents. In the same way, the quantum vacuum is filled with tiny, rapid fluctuations of energy, as particles and antiparticles pop in and out of existence. These fleeting particles, known as virtual particles, are a direct consequence of the uncertainty principle, which allows energy to be borrowed from the vacuum for incredibly short periods of time. Zero-point energy has profound implications for our understanding of the universe. For one, it suggests that empty space is not truly empty but teeming with potential. This energy is thought to contribute to phenomena like the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force due to the fluctuations of the vacuum between them. It's a striking demonstration of how the quantum vacuum can influence the physical world, but the implications go even further. Some theories propose that zero-point energy could be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If the vacuum energy is indeed responsible for this expansion, it would mean that the very fabric of space itself is imbued with an energy that shapes the cosmos on the largest scales. However, harnessing zero-point energy remains a tantalizing yet elusive goal. While the energy density of the vacuum is immense, extracting usable energy from it is a challenge that pushes the boundaries of our current technology and understanding. Some speculative ideas, like advanced propulsion systems or energy extraction devices, have been proposed, but they remain firmly in the realm of theoretical exploration. The quantum vacuum and zero-point energy remind us that even in what we perceive as emptiness, there's a hidden richness waiting to be uncovered. These concepts not only deepen our understanding of quantum fields, but also open up new avenues for exploring the fundamental nature of reality. Next, we'll explore how spontaneous symmetry breaking in quantum fields plays a crucial role in shaping the universe as we know it. Now, let's turn our attention to a concept that might sound abstract, but is absolutely fundamental to the structure of our universe: spontaneous symmetry breaking. This phenomenon occurs when a system that is symmetric under certain conditions suddenly loses that symmetry, leading to profound consequences in the quantum world. One of the most famous examples of this is the Higgs mechanism, which plays a crucial role in giving particles their mass and in turn shaping the universe as we know it. To understand spontaneous symmetry breaking, let's start with a simple analogy. Imagine a pencil perfectly balanced on its tip. In this state, the pencil is symmetric. It looks the same from every angle. But the moment the pencil falls, it chooses a specific direction to lean, breaking that symmetry. In the quantum world, something similar happens with fields. A quantum field might start in a symmetric state, but as conditions change, it can fall into a less symmetric state, leading to new physical phenomena. The Higgs field is a prime example of this. In the early universe, the Higgs field was symmetric, meaning it had the same properties in all directions. But as the universe cooled, the field underwent a phase transition, much like water freezing into ice. This transition caused the Higgs field to break its symmetry, settling into a state where it could interact with other particles. These interactions are what give particles like electrons and quarks their mass. Without this process, particles would remain massless, and the universe as we know it simply wouldn't exist. But the implications of spontaneous symmetry breaking go far beyond the Higgs field. It's a principle that appears in many areas of physics, from the behavior of magnets to the formation of cosmic structures. In magnets, for instance, the alignment of atomic spins breaks symmetry, creating a magnetic field. In the early universe, symmetry breaking may have played a role in the formation of galaxies and other large-scale structures, as tiny fluctuations in quantum fields were amplified over time. What's truly fascinating is how this process ties into the broader picture of the universe. Spontaneous symmetry breaking is not just a quirk of quantum fields. It's a driving force behind the diversity and complexity we see in the cosmos. It's the reason particles have mass, forces behave the way they do, and the universe has the structure it does. Without it, the universe would be a very different place. As we continue to explore the mysteries of quantum fields, spontaneous symmetry breaking remains a key piece of the puzzle. It's a reminder that even the most fundamental aspects of reality are shaped by subtle yet powerful processes. Next, we'll dive into supersymmetry, a theory that takes the idea of symmetry in quantum fields to an entirely new level, proposing a hidden connection between particles that could revolutionize our understanding of the universe. Now, let's shift our focus to a theory that takes the concept of symmetry in quantum fields to an entirely new dimension: supersymmetry, often abbreviated as SUSY. This groundbreaking idea proposes a deep and elegant connection between two fundamental classes of particles: fermions, which make up matter, and bosons, which carry forces. According to supersymmetry, every particle we know has a hidden superpartner, a mirror image with different properties but linked by a profound symmetry. To put it simply, supersymmetry suggests that the universe operates on a level of balance we've yet to fully uncover. For example, the electron, a fermion, would have a superpartner called the selectron, a boson. Similarly, the photon, a boson, would have a fermionic counterpart called the photino. These superpartners aren't just theoretical curiosities. They could hold the key to solving some of the biggest mysteries in physics. One of the most compelling reasons physicists are drawn to supersymmetry is its potential to address unanswered questions in the standard model of particle physics. For instance, the standard model doesn't explain why the Higgs boson has the mass it does, or why gravity is so much weaker than the other fundamental forces. SUSY offers elegant solutions to these puzzles. By introducing superpartners, the theory could stabilize the mass of the Higgs boson and even provide a candidate for dark matter, the invisible substance that makes up most of the universe's mass. But supersymmetry isn't just about solving problems, it's also about unification. The theory hints at a deeper connection between all the forces and particles in nature, suggesting that at very high energies, such as those present in the early universe, these superpartners would have been indistinguishable from their counterparts. This symmetry could be a clue to how the universe began and how its fundamental forces emerged from a single, unified framework. Despite its elegance, supersymmetry has yet to be confirmed experimentally. Particle colliders like the Large Hadron Collider have searched for evidence of superpartners, but so far they've remained elusive. This doesn't mean SUSY is wrong. It could simply mean that superpartners are heavier than we've been able to detect, or that they interact in ways we haven't yet observed. The search continues, and with each new experiment, we get closer to uncovering whether this beautiful symmetry truly exists. Supersymmetry reminds us that the universe might be far more interconnected than we realize. It challenges us to think beyond the particles we know and imagine a hidden layer of reality waiting to be discovered. As we move forward, we'll explore another fascinating idea, string theory, and see how it ties quantum fields to the very fabric of spacetime. Now, let's take a step into a realm where the very fabric of reality is reimagined string theory. This theory doesn't just build on quantum fields, it transforms them entirely. Instead of particles being the fundamental building blocks of the universe, string theory proposes that everything is made up of tiny, vibrating strings. These strings aren't just floating around, they exist in higher dimensional fields, vibrating at different frequencies to create the particles and forces we observe. Think of it like this: if quantum fields are the stage, strings are the actors, each playing a unique role depending on how they vibrate. A string vibrating one way might become an electron, while another vibration could produce a photon. This idea takes the concept of quantum fields to a whole new level, suggesting that the universe is like a cosmic symphony, with strings as the notes that compose the music of reality. One of the most fascinating aspects of string theory is its potential to unify all the fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. In the framework of string theory, these forces aren't separate entities but different expressions of the same underlying mechanism. For example, gravity, which has always been the odd one out in quantum field theory, finds a natural place in string theory. The graviton, the hypothetical particle that carries gravitational force, emerges as a specific vibration of a string, seamlessly integrating gravity into the quantum world. But string theory doesn't stop there. It also introduces the idea of extra dimensions beyond the three spatial dimensions and time we're familiar with. These higher dimensions aren't just theoretical fluff. They're essential for the strings to vibrate in the complex ways needed to produce the diversity of particles and forces in the universe. Imagine a guitar string that can vibrate not just up and down, but in multiple directions we can't even see. These extra dimensions could be curled up so tightly that they're invisible to us, yet they play a crucial role in shaping the universe. String theory also offers a tantalizing connection to quantum fields. In this framework, quantum fields can be thought of as the collective behavior of these vibrating strings. Just as waves on the surface of a pond are made up of countless water molecules, quantum fields emerge from the interactions of countless strings. This perspective bridges the gap between the microscopic world of strings and the macroscopic world of fields, offering a unified picture of reality. However, like supersymmetry, string theory remains unproven. It's a mathematically elegant framework, but it's also incredibly complex, making it difficult to test experimentally. Yet, its potential to explain the deepest mysteries of the universe, from the nature of black holes to the origins of spacetime itself, keeps physicists intrigued. As we continue to explore the implications of string theory, we're reminded that the universe might be far stranger and more interconnected than we've ever imagined. With this in mind, let's turn our attention to another mind-bending idea, the multiverse, and see how quantum fields might give rise to an infinite tapestry of universes, each with its own unique set of rules and possibilities. Now, let's venture into one of the most mind-expanding ideas in modern physics, the multiverse. Imagine a reality where our universe isn't the only one, but just one of countless others, each with its own unique set of physical laws and constants. This isn't science fiction, it's a serious scientific theory rooted in the behavior of quantum fields. At the heart of this idea is the concept of eternal inflation. Picture the early universe as a rapidly expanding foam with quantum fields driving this expansion. In some regions, these fields settle into stable states, creating what we call bubble universes. Each bubble is like a separate universe with its own distinct properties. Some might have stronger gravity, while others might have entirely different particles or forces. Our universe could be just one bubble in an infinite cosmic sea. Quantum fields play a crucial role here. They don't just define the particles and forces within a single universe, they also determine how these bubble universes form and evolve. Think of quantum fields as the architects of the multiverse, shaping the fabric of reality in ways that are both subtle and profound. For instance, fluctuations in these fields during the early moments of inflation could have seeded the formation of countless universes, each with its own unique history and destiny. One fascinating aspect of this theory is the idea that the laws of physics we observe in our universe might not be universal. In other bubble universes, the constants of nature, like the speed of light or the strength of gravity, could be entirely different. This raises profound questions about the nature of reality. Are the laws of physics we take for granted just one possibility among an infinite array? And if so, what does that mean for our understanding of existence? But how do we even begin to test such a theory? While direct evidence for the multiverse remains elusive, some physicists suggest that the cosmic microwave background, the afterglow of the Big Bang, might hold clues. Tiny anomalies in this radiation could be the fingerprints of collisions between our universe and neighboring bubbles. It's a long shot, but it's one of the few ways we might glimpse the multiverse from within our own cosmic bubble. The multiverse theory also ties back to quantum fields in another intriguing way. In some versions of the theory, every possible outcome of a quantum event spawns a new universe. This means that every time a particle decays or a measurement is made, the universe splits into multiple branches, each representing a different outcome. It's a dizzying thought, but it underscores the deep connection between quantum fields and the structure of reality itself. As we ponder the multiverse, we're left with more questions than answers. Could there be other versions of us out there, living in universes where history unfolded differently? Or are we truly alone in this vast cosmic landscape? These are the kinds of questions that push the boundaries of science and imagination, reminding us that the universe or multiverse is far stranger and more wondrous than we've ever imagined. With this in mind, let's shift our focus to another profound mystery: dark energy, and explore how quantum fields might hold the key to understanding the universe's accelerating expansion. Now, let's turn our attention to one of the most perplexing mysteries in modern cosmology: dark energy. This enigmatic force is believed to be responsible for the universe's accelerating expansion. But what exactly is it, and how does it connect to the quantum fields we've been exploring? To understand this, we need to dive into the concept of vacuum energy, a phenomenon deeply rooted in the behavior of quantum fields. At its core, vacuum energy is the energy that exists in empty space, even when it seems like there's nothing there. According to quantum field theory, the vacuum isn't truly empty. Instead, it's a seething, dynamic sea of virtual particles that constantly pop in and out of existence. These fleeting particles are manifestations of quantum fields, and their activity generates a baseline energy that permeates the entire universe. This energy is what we call vacuum energy, and it's thought to be a key player in the story of dark energy. But how does vacuum energy relate to the universe's expansion? Imagine the universe as a balloon being inflated. As it expands, the space between galaxies grows, and the energy within that space, vacuum energy, exerts a kind of pressure. Unlike ordinary matter or radiation, which lose energy as the universe expands, vacuum energy remains constant. This means that as the universe grows larger, the influence of vacuum energy becomes more dominant, pushing galaxies apart at an ever-increasing rate. This is the essence of dark energy's role in cosmic acceleration. The connection between quantum fields and dark energy becomes even more intriguing when we consider the scale of the universe. Quantum field theory predicts that vacuum energy should be incredibly dense, so dense, in fact, that it should cause the universe to expand at a rate far faster than what we observe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Why is the observed value of dark energy so much smaller than what quantum field theory suggests? Some physicists propose that there might be undiscovered mechanisms at play, perhaps involving new quantum fields or interactions that we haven't yet detected. Another fascinating idea is that dark energy might not be constant after all. Some theories suggest that it could vary over time or space, influenced by the dynamics of quantum fields. For instance, certain quantum fields might undergo phase transitions, similar to how water turns into ice, altering the properties of dark energy in the process. If this is true, it could mean that the universe's expansion rate has changed over its history and might continue to evolve in the future. While the exact nature of dark energy remains elusive, its connection to quantum fields offers a tantalizing glimpse into the deeper workings of the cosmos. By studying the behavior of these fields, we might one day uncover the secrets behind the universe's accelerating expansion, and in doing so, gain a better understanding of the fundamental forces that shape reality. As we continue our journey through the mysteries of quantum fields, let's explore another intriguing possibility, dark matter, and how it might be linked to the same quantum fields that give rise to particles, forces, and even the fabric of space itself. Now, shifting our focus to another cosmic enigma, let's delve into the mysterious realm of dark matter and its potential connection to quantum fields. While dark energy drives the universe's expansion, dark matter is believed to be the invisible scaffolding that holds galaxies together. But what exactly is dark matter, and how might it be tied to the quantum fields we've been discussing? The answer could lie in undiscovered fields that operate beyond the reach of our current understanding. One compelling theory suggests that dark matter might be composed of particles arising from hidden quantum fields. These fields could exist alongside the ones we already know, such as the Higgs field or electromagnetic fields, but interact so weakly with ordinary matter that they've remained undetected. One candidate for such a particle is the action, a hypothetical particle predicted by certain extensions of quantum field theory. Actions are thought to be incredibly light and nearly invisible to our detectors, making them a perfect fit for the elusive nature of dark matter. The idea of action stems from attempts to solve a puzzle in particle physics known as the strong charge parity problem. In the process, physicists proposed the existence of a new quantum field that would give rise to actions. If actions exist, they could permeate the universe, forming a kind of cosmic fog that interacts only gravitationally with ordinary matter. This would explain why dark matter doesn't emit light or interact with electromagnetic forces, yet still exerts a gravitational pull strong enough to shape galaxies and galaxy clusters. Another intriguing possibility is that dark matter might be linked to what physicists call hidden sector fields. These are quantum fields that exist in a separate sector of reality, interacting with our familiar particles and forces only through gravity or extremely weak interactions. Hidden sector fields could give rise to a whole family of particles that make up dark matter, each with unique properties that set them apart from the particles in the standard model. Exploring these hidden sectors could open up entirely new avenues for understanding the universe's invisible architecture. What makes these theories so fascinating is their potential to bridge the gap between the known and the unknown. By connecting dark matter to quantum fields, we might uncover a deeper layer of reality that explains not only the behavior of galaxies, but also the fundamental nature of matter itself. Experiments are already underway to detect actions and other dark matter candidates, using highly sensitive instruments designed to pick up the faintest signals from these elusive particles. As we continue to probe the mysteries of dark matter, the role of quantum fields becomes increasingly central. Whether through actions, hidden sectors, or other yet-to-be-discovered phenomena, the interplay between these fields and dark matter could hold the key to understanding one of the universe's greatest puzzles. And with every new discovery, we move closer to unraveling the intricate tapestry of reality itself. With this in mind, let's turn our attention to another profound question: how quantum fields might help us reconcile the forces of nature, particularly the elusive connection between quantum mechanics and gravity. Now, as we venture deeper into the mysteries of the universe, let's explore one of the most profound challenges in modern physics: the quest to unify quantum field theory with gravity. While quantum field theory has been incredibly successful in describing three of the four fundamental forces, electromagnetism, the strong force, and the weak force, gravity remains the odd one out. Described by Einstein's theory of general relativity, gravity operates on a completely different framework, and reconciling it with the quantum world has proven to be one of the greatest puzzles in science. One promising approach to this challenge is loop quantum gravity. This theory attempts to describe gravity in terms of quantum fields by proposing that space-time itself is made up of tiny, discrete loops. Imagine space-time as a fabric woven from these loops, each representing the smallest possible unit of space and time. In this framework, gravity emerges from the interactions of these loops, offering a way to bridge the gap between the smooth, continuous space-time of general relativity and the discrete, quantized nature of quantum mechanics. While still a work in progress, loop quantum gravity provides a fascinating perspective on how the universe might operate at its most fundamental level. Another intriguing idea is emergent gravity, which suggests that gravity isn't a fundamental force at all, but rather an emergent phenomenon arising from more basic quantum processes. Think of it like how temperature emerges from the collective motion of molecules. Gravity could similarly arise from the interactions of quantum fields. This theory challenges our traditional understanding of gravity as a force and instead frames it as a byproduct of deeper quantum dynamics. If true, it could revolutionize our understanding of the universe, showing that gravity is not something separate but woven into the very fabric of quantum reality. These theories, while still speculative, highlight the creative and ambitious efforts of physicists to solve the quantum gravity puzzle. By exploring loop quantum gravity and emergent gravity, we're not just trying to unify two theories, we're attempting to rewrite the rules of reality itself. And while the answers remain elusive, each step forward brings us closer to understanding how the universe truly works at its deepest levels. With this in mind, let's shift our focus to another fascinating phenomenon that arises from the interplay of quantum fields, the Casimir effect, a striking demonstration of how the vacuum of space is anything but empty. Now, let's turn our attention to a phenomenon that vividly illustrates the strange and active nature of the quantum vacuum, the Casimir effect. At first glance, the vacuum of space might seem like an empty void, but in the quantum world, it's anything but. Quantum fields are constantly fluctuating, even in what we perceive as empty space, and these fluctuations give rise to some truly fascinating effects. The Casimir effect is one of the most striking examples of this. Imagine two uncharged, parallel metal plates placed extremely close to each other in a vacuum. According to classical physics, nothing should happen, no force should act between them. But in the quantum realm, the story is very different. The space between the plates restricts the kinds of quantum fluctuations that can occur, while the space outside the plates allows for a wider range of fluctuations. This imbalance creates a subtle but measurable force pushing the plates together. This force, predicted by Dutch physicist Hendrik Casimir in the 1940s, is a direct result of the quantum vacuum's energy. What makes the Casimir effect so remarkable is that it provides tangible evidence of the quantum vacuum's activity. It shows that empty space is teeming with virtual particles popping in and out of existence, and these fluctuations can have real physical consequences. The effect has been experimentally confirmed with incredible precision, and it's not just a theoretical curiosity. It has practical implications in fields like nanotechnology, where understanding these tiny forces is crucial. The Casimir effect also ties back to our earlier discussions about zero-point energy and the quantum vacuum. It's a vivid reminder that the vacuum isn't empty but filled with a dynamic sea of energy and fluctuations. This phenomenon challenges our everyday intuition about space and forces, showing once again how quantum fields shape the fabric of reality in ways that are both subtle and profound. As we continue to explore the mysteries of quantum fields, the Casimir effect serves as a powerful example of how even the most seemingly empty spaces are alive with activity. Next, we'll delve into another fascinating aspect of quantum fields, quantum entanglement, and how it connects to the underlying fabric of the universe. Now, shifting our focus to one of the most mind-bending phenomena in quantum physics, let's dive into the world of quantum entanglement and its deep connection to quantum fields. Quantum entanglement is often described as a spooky action at a distance, a phrase coined by Albert Einstein to capture its bizarre nature. But what exactly is entanglement, and how do quantum fields make it possible? At its core, entanglement occurs when two or more particles become so deeply linked that the state of one instantly influences the state of the other, no matter how far apart they are. This connection isn't mediated by any known force or signal traveling through space. It's a direct result of the underlying quantum fields that govern the behavior of particles. These fields create a kind of invisible web that ties entangled particles together, allowing them to share information instantaneously. To understand how this works, let's break it down. Quantum fields are the foundation of all particles. When particles interact, their quantum fields become intertwined, creating a shared state. Even if these particles are later separated by vast distances, their fields remain connected. This means that measuring one particle immediately determines the state of its entangled partner, as if they're still in direct contact. It's a phenomenon that defies our classical understanding of space and time, and it's all made possible by the intricate dance of quantum fields. The implications of entanglement are profound, especially in the realms of quantum communication and computing. In quantum communication, entangled particles can be used to create ultra-secure networks. Because any attempt to intercept or measure the particles would disturb their entangled state, it's possible to detect eavesdropping instantly. This makes quantum communication a potential game-changer for secure data transmission. In quantum computing, entanglement allows for the creation of qubits, quantum bits that can exist in multiple states simultaneously. This enables quantum computers to perform complex calculations at speeds far beyond the capabilities of classical computers. By harnessing the power of entangled quantum fields, researchers are working to revolutionize fields like cryptography, materials science, and artificial intelligence. But entanglement isn't just a tool for technology, it's also a window into the fundamental nature of reality. It challenges our understanding of locality, suggesting that the universe might be far more interconnected than we ever imagined. Quantum fields, with their ability to link particles across vast distances, hint at a deeper layer of unity in the cosmos. As we continue to explore the mysteries of quantum fields, entanglement stands as a testament to their extraordinary power. It's a phenomenon that bridges the gap between the microscopic world of particles and the vast expanse of the universe, reminding us that reality is far stranger and more interconnected than it appears. Next, we'll venture into the holographic principle, a theory that suggests the universe itself might be encoded on quantum fields like a cosmic hologram. Now, let's take a step into one of the most fascinating and mind-expanding ideas in modern physics, the holographic principle. This theory suggests that the entire universe, with all its complexity and vastness, might actually be a hologram encoded on quantum fields. Imagine that everything we see, from the stars in the sky to the ground beneath our feet, could be a projection of information stored on a two-dimensional surface. It's a concept that sounds like science fiction, but it's rooted in some of the most cutting-edge research in physics. The holographic principle emerged from the study of black holes, those mysterious regions of space where gravity is so strong that nothing, not even light, can escape. Physicists discovered that the information about everything that falls into a black hole isn't lost forever. It's somehow encoded on the black hole's event horizon, the boundary beyond which nothing can return. This realization led to the idea that the universe itself might work in a similar way, with all the information about three-dimensional space being stored on a two-dimensional surface. But how does this connect to quantum fields? Quantum fields are the fundamental fabric of reality, and they're everywhere, even in the vacuum of space. According to the holographic principle, these fields might act like a kind of cosmic hard drive, storing the information needed to project the three-dimensional universe we experience. It's as if the universe is a hologram, with quantum fields serving as the code that generates the image. This idea also ties into string theory, which proposes that the fundamental building blocks of the universe are tiny, vibrating strings. In string theory, the holographic principle suggests that these strings and their interactions could be described by a lower dimensional theory, effectively reducing the complexity of the universe to a simpler, more manageable framework. It's a bold idea that could help unify our understanding of gravity and quantum mechanics, two forces that have proven notoriously difficult to reconcile. The implications of the holographic principle are staggering. If the universe is indeed a hologram, it would mean that our perception of reality is just a surface-level projection of deeper, more fundamental processes. It challenges our understanding of space, time, and even the nature of existence itself. Could it be that everything we experience is just a shadow of a more profound truth encoded in quantum fields? As we continue to explore this theory, we're reminded once again of the extraordinary power of quantum fields to shape our understanding of the cosmos. The holographic principle invites us to rethink what we know about reality, offering a glimpse into a universe that's far more interconnected and mysterious than we ever imagined. Next, we'll delve into how quantum fields behave in curved spacetime, exploring their role in extreme environments like black holes and the Big Bang. Now, shifting our focus to the behavior of quantum fields in extreme environments, let's explore how these fundamental entities interact with the fabric of spacetime itself. Quantum field theory in curved spacetime is a fascinating area of study that bridges the gap between quantum mechanics and Einstein's theory of general relativity. It examines how quantum fields, which are the building blocks of reality, behave when spacetime isn't flat but instead warped by massive objects like black holes or the intense conditions of the early universe. To understand this, let's start with a simple idea. In our everyday experience, spacetime is relatively flat and uniform. But when you introduce massive objects like black holes or consider the universe during the Big Bang, spacetime becomes curved. This curvature isn't just a geometric curiosity. It fundamentally changes how quantum fields operate. For example, near a black hole, the immense gravitational pull warps spacetime so severely that it alters the behavior of particles and fields. What we might think of as straightforward quantum interactions in flat spacetime become far more complex and intriguing in these extreme conditions. One of the most striking phenomena in curved spacetime is Hawking radiation, which we touched on earlier. Near a black hole's event horizon, quantum fields are stretched and distorted by the intense gravity. This distortion creates pairs of particles and antiparticles, with one falling into the black hole and the other escaping as radiation. This process, predicted by Stephen Hawking, shows how quantum fields in curved spacetime can lead to surprising and counterintuitive outcomes, like black holes slowly losing mass over time. But the story doesn't end with black holes. During the Big Bang, the universe was in a state of rapid expansion, with spacetime itself stretching and evolving at an incredible rate. Quantum fields in this environment would have behaved very differently than they do today. For instance, fluctuations in these fields during the early universe are thought to have seeded the large-scale structure of the cosmos, leading to the formation of galaxies and galaxy clusters. This connection between quantum fields and the birth of the universe highlights just how deeply intertwined these concepts are. What makes quantum field theory in curved spacetime so challenging and so exciting is that it forces us to rethink our understanding of both quantum mechanics and gravity. In flat spacetime, quantum fields are well understood, but when spacetime curves, the rules change. This has led physicists to develop new mathematical tools and frameworks to describe these interactions, pushing the boundaries of our knowledge. As we continue to explore this theory, we're reminded of the profound interplay between the very small and the very large. Quantum fields, which govern the behavior of particles at the smallest scales, also play a crucial role in shaping the universe on the grandest scales. From the intense gravity of black holes to the explosive energy of the Big Bang, these fields are at the heart of some of the most dramatic events in the cosmos. Next, we'll dive into the Unruh effect, another fascinating consequence of quantum fields in extreme conditions, and see how it connects to our understanding of relativity and the nature of reality itself. Now, let's turn our attention to a phenomenon that challenges our everyday understanding of reality, the Unruh effect. This intriguing concept reveals how the perception of quantum fields can change dramatically depending on the observer's motion. Specifically, it shows that an accelerating observer will perceive what appears to be a vacuum in flat spacetime as a warm bath of thermal radiation. This effect, named after physicist William Unruh, bridges the gap between quantum field theory and Einstein's theory of relativity, offering profound insights into the nature of reality itself. To grasp the Unruh effect, imagine you're floating in empty space far from any massive objects. In this scenario, you'd perceive the quantum fields around you as a vacuum, a state of emptiness with no particles. But if you were to accelerate, something extraordinary happens. From your perspective, the vacuum would no longer seem empty. Instead, you detect a faint glow of thermal radiation, as if you were surrounded by a warm, invisible heat source. This radiation isn't an illusion, it's a direct consequence of your acceleration through the quantum fields. The key to understanding this lies in the relationship between motion and the quantum vacuum. In flat spacetime, a stationary observer sees the vacuum as empty because the quantum fields are in their lowest energy state. However, an accelerating observer experiences spacetime differently. Their motion causes the quantum fields to appear distorted, creating what's known as a thermal bath of particles. This effect is analogous to how an accelerating car might make the road ahead seem to curve, even though it's actually straight. In both cases, the observer's motion changes their perception of the environment. The Unruh effect has deep implications for our understanding of relativity and quantum mechanics. It suggests that the concept of a vacuum isn't absolute but depends on the observer's frame of reference. What one observer sees as empty space, another might perceive as filled with particles. This relativity of the vacuum challenges our intuitive notions of reality and highlights the intricate interplay between motion, spacetime, and quantum fields. Interestingly, the Unruh effect shares a close connection with Hawking radiation, which we discussed earlier. Both phenomena arise from the interaction between quantum fields and extreme conditions, whether it's the intense gravity near a black hole or the rapid acceleration of an observer. In both cases, what appears to be empty space is revealed to be teeming with activity, driven by the underlying quantum fields. The Unruh effect also raises fascinating questions about the nature of temperature and energy in the universe. For instance, if an accelerating observer detects thermal radiation, does that mean energy is being created out of nothing? The answer lies in the fact that the energy isn't being created but rather redistributed. The observer's acceleration effectively shifts the quantum fields, causing them to appear as thermal radiation. This subtle distinction underscores the elegance of quantum field theory and its ability to explain seemingly paradoxical phenomena. As we explore the Unruh effect, we're reminded once again of the profound unity between the very small and the very large. Quantum fields, which govern the behavior of particles at the tiniest scales, also shape our understanding of motion, gravity, and the fabric of space-time itself. This effect not only deepens our appreciation for the complexities of the universe, but also inspires new questions about the nature of reality and the limits of our perception. Next, we'll delve into the connection between the Unruh effect and Hawking radiation, uncovering how these two phenomena are intertwined and what they reveal about the fundamental nature of quantum fields in extreme environments. Now, let's take a closer look at how the Unruh effect ties into one of the most fascinating predictions in modern physics, Hawking radiation. This phenomenon, named after the legendary physicist Stephen Hawking, reveals how black holes aren't entirely black but instead emit a faint glow of radiation. At its core, Hawking radiation is a direct consequence of quantum fields behaving in the extreme gravitational environment near a black hole, and it shares a deep connection with the Unruh effect we just explored. To understand Hawking radiation, picture a black hole's event horizon, the point of no return where gravity is so strong that not even light can escape. In the vacuum of space, quantum fields are constantly fluctuating, creating pairs of particles and antiparticles that pop in and out of existence. Normally, these pairs annihilate each other almost instantly. But near a black hole's event horizon, something extraordinary happens. If a particle-antiparticle pair forms right at the edge, one particle might fall into the black hole while the other escapes into space. The escaping particle is what we detect as Hawking radiation. This process is eerily similar to the Unruh effect. Just as an accelerating observer perceives thermal radiation in what appears to be a vacuum, an observer near a black hole detects Hawking radiation due to the intense gravitational field. Both phenomena arise from the way quantum fields interact with extreme conditions, whether it's acceleration or gravity. In both cases, what seems like empty space is actually teeming with activity, driven by the underlying quantum fields. The connection between the Unruh effect and Hawking radiation goes even deeper when we consider the concept of temperature. Just as an accelerating observer detects a thermal bath of particles, a black hole emits Hawking radiation with a temperature proportional to its surface gravity. This means black holes aren't just cold, lifeless objects. They have a temperature and, over time, can lose mass and energy through this radiation. This discovery revolutionized our understanding of black holes, showing that they're not eternal but can slowly evaporate over unimaginable timescales. But how does this relate to black hole thermodynamics? The answer lies in the idea that black holes have entropy, a measure of disorder or information. Hawking radiation suggests that black holes aren't just gravitational monsters, but also thermodynamic systems with properties like temperature and entropy. This insight bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that have long resisted unification. It also raises profound questions about the fate of information that falls into a black hole, a puzzle known as the black hole information paradox. The interplay between Hawking radiation and the Unruh effect highlights the elegance of quantum field theory in explaining seemingly unrelated phenomena. Both effects show how the perception of reality depends on the observer's frame of reference, whether they're accelerating through space or hovering near a black hole. They remind us that the quantum vacuum is far from empty. It's a dynamic, ever-changing sea of energy and particles, shaped by the forces of motion and gravity. As we reflect on these connections, we're left with a deeper appreciation for the unity of the universe. Quantum fields, which govern the behavior of particles at the smallest scales, also shape the behavior of the largest and most mysterious objects in the cosmos. The Unruh effect and Hawking radiation are two sides of the same coin, revealing the profound interplay between quantum mechanics, relativity, and the nature of reality itself. Next, we'll explore how quantum fields shaped the early universe, diving into the role they played during the Big Bang and the formation of cosmic structures. This journey will take us even further into the mysteries of quantum fields and their impact on the cosmos. Now, let's journey back in time to the very beginning, the early universe, where quantum fields played a pivotal role in shaping everything we see today. Imagine the universe just moments after the Big Bang, a seething, chaotic soup of energy and particles. At this stage, quantum fields weren't just background players. They were the architects of the cosmos, driving processes like inflation, reheating, and the formation of cosmic structures. Inflation is one of the most dramatic events in the universe's history. Picture this: in a fraction of a second, the universe expanded exponentially, stretching from a size smaller than an atom to something unimaginably vast. This rapid expansion wasn't driven by ordinary matter or energy, but by a quantum field known as the inflaton field. As this field evolved, it released energy, causing space itself to stretch at an incredible rate. This process smoothed out the universe, making it remarkably uniform on large scales, while also planting the seeds for future structures like galaxies and galaxy clusters. But inflation couldn't last forever. As the inflaton field decayed, its energy was transferred to other quantum fields, heating up the universe in a process called reheating. Think of it as the universe's reboot, where the cold, empty space left after inflation was filled with particles and radiation. This marked the beginning of the hot Big Bang phase, where the universe became a dense, energetic plasma. Quantum fields like the Higgs field began to take center stage, giving mass to particles and setting the stage for the formation of matter as we know it. As the universe continued to expand and cool, tiny fluctuations in the quantum fields imprinted during inflation began to grow. These fluctuations were like ripples on a pond, but instead of water, they were variations in density and temperature. Over billions of years, gravity amplified these ripples, pulling matter together to form the first stars, galaxies, and eventually the vast cosmic web we observe today. Without these quantum fluctuations, the universe would have remained a featureless void, devoid of the structures that make it so rich and dynamic. The role of quantum fields in the early universe doesn't stop there. They also influence the distribution of dark matter, an invisible substance that makes up most of the universe's mass. While we can't see dark matter directly, its gravitational effects reveal its presence, shaping the large-scale structure of the cosmos. Some theories suggest that dark matter might be connected to yet undiscovered quantum fields, adding another layer of mystery to this already fascinating story. What's truly remarkable is how quantum fields, which operate on the tiniest scales, had such a profound impact on the largest scales of the universe. From the rapid expansion of inflation to the intricate dance of particles during reheating, and finally to the formation of galaxies and clusters, quantum fields were the invisible hands guiding the universe's evolution. They remind us that the cosmos is deeply interconnected, with the smallest building blocks shaping the grandest structures. As we reflect on the early universe, we're left with a sense of awe at the elegance of quantum field theory. It not only explains the behavior of particles, but also provides a framework for understanding the universe's birth and growth. Next, we'll delve into the quantum measurement problem, exploring how quantum fields interact with observers and the profound questions this raises about the nature of reality. Stay tuned as we continue unraveling the mysteries of quantum fields and their role in the cosmos. Now, let's shift our focus to one of the most puzzling aspects of quantum field theory, the quantum measurement problem. This is where the strange and counterintuitive nature of quantum mechanics truly comes to the forefront, raising profound questions about the role of observers in shaping reality. At its core, the measurement problem asks, how does a quantum system which exists in a superposition of states suddenly choose a single outcome when measured? And what role do quantum fields play in this process? To understand this, let's start with a simple example. Imagine a quantum particle like an electron that can exist in multiple states simultaneously, a phenomenon known as superposition. According to quantum field theory, this electron is an excitation of the electron field, and its behavior is governed by the probabilities encoded in the field. But here's the catch: when we measure the electron, it appears to collapse into a single state. Why does this happen, and who or what causes this collapse? This is where the measurement problem comes into play. In the Copenhagen interpretation, one of the most widely discussed frameworks, the act of measurement by an observer is what causes the collapse of the quantum state. In other words, the observer's interaction with the quantum field forces it to choose a definite outcome, but this raises even more questions. What counts as an observer? Is it a conscious being, a measuring device, or something else entirely? And how does this process align with the continuous, probabilistic nature of quantum fields? Some interpretations, like the many worlds theory, take a different approach. Instead of a collapse, they suggest that every possible outcome of a quantum measurement actually occurs, but in separate, branching universes. In this view, quantum fields don't collapse, they simply evolve in all possible ways, creating a multiverse of realities. While this idea is fascinating, it also leaves us wondering, how do we reconcile these interpretations with our everyday experience of a single, definite reality? Another perspective comes from decoherence theory, which explains how interactions between a quantum system and its environment lead to the appearance of collapse. In this framework, quantum fields are constantly interacting with their surroundings, causing superpositions to decohere and appear as if they've collapsed into a single state. This doesn't solve the measurement problem entirely, but it does provide a way to understand why we observe definite outcomes in a world governed by quantum probabilities. The quantum measurement problem isn't just a theoretical curiosity, it has real implications for how we understand the universe. It challenges our notions of objectivity, suggesting that the act of observation might play a fundamental role in shaping reality. It also raises questions about the nature of quantum fields themselves. Are they truly independent of observers, or do they require some form of interaction to manifest the world we see? As we grapple with these questions, we're reminded of the deep mysteries that quantum field theory continues to unravel. The measurement problem invites us to rethink our understanding of reality, blurring the lines between the observer and the observed. Next, we'll explore even more speculative ideas, diving into theories that link quantum fields to consciousness itself. Stay with us as we venture further into the enigmatic world of quantum fields and their profound implications for the nature of existence. Now, let's take a step into one of the most intriguing and speculative areas of quantum field theory, its potential connection to consciousness. This is where science meets philosophy, as we explore theories that suggest quantum fields might play a role in the very fabric of our awareness. Could consciousness itself be rooted in the behavior of quantum fields? Let's dive into this fascinating idea. One of the most well-known theories in this space is ORCH, or short for Orchestrated Objective Reduction. Proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, this theory suggests that consciousness arises from quantum processes occurring within the brain's neurons. Specifically, it points to microtubules, tiny structures within neurons, as the site where quantum field interactions could give rise to conscious experience. According to Orch, these quantum processes are orchestrated by the brain, and their collapse into definite states generates moments of awareness. While this theory is highly speculative and debated, it opens up a provocative question. Could quantum fields be the bridge between the physical brain and the subjective experience of consciousness? Another perspective comes from panpsychism, a philosophical view that suggests consciousness is a fundamental property of the universe, much like mass or charge. In this framework, quantum fields might not just describe particles and forces, they could also encode the building blocks of consciousness itself. Panpsychism doesn't necessarily rely on quantum mechanics, but some versions of the theory propose that the probabilistic, interconnected nature of quantum fields could provide a natural foundation for consciousness to emerge. This idea challenges us to rethink the boundaries between mind and matter, suggesting that the universe itself might be imbued with some form of awareness. These theories, while speculative, push the boundaries of our understanding. They invite us to consider whether quantum fields could be more than just the scaffolding of physical reality. They might also hold the key to understanding the nature of consciousness. But as we explore these ideas, we're also reminded of the challenges. How do we test such theories? What evidence would we need to connect quantum fields to the subjective experience of being aware? These questions remain open, but they highlight the profound mysteries that quantum field theory continues to uncover. As we ponder these possibilities, we're left with a sense of wonder. The idea that quantum fields might be linked to consciousness blurs the line between the observer and the observed, suggesting that our awareness could be deeply intertwined with the fabric of the universe itself. Next, we'll shift our focus to a more concrete application of quantum fields, exploring how they describe phenomena in condensed matter physics. Stay with us as we continue to unravel the mysteries of quantum fields and their role in shaping the world around us. Now, let's turn our attention to a fascinating and practical application of quantum fields' condensed matter physics. This is where the abstract world of quantum fields meets the tangible, everyday materials that shape our lives. From superconductors to exotic states of matter, quantum fields provide the framework to understand some of the most intriguing phenomena in the physical world. One of the most striking examples is superconductivity, a phenomenon where certain materials can conduct electricity without any resistance when cooled to extremely low temperatures. At the heart of this behavior lies the concept of quantum fields. In a superconductor, electrons pair up and move in a coordinated way, forming what's known as a Cooper pair. These pairs are described by a quantum field that extends throughout the material, allowing them to flow seamlessly without losing energy. This quantum field isn't just a mathematical tool. It's a real, physical entity that governs the behavior of electrons, enabling the remarkable properties of superconductors. From MRI machines to maglev trains, the applications of superconductivity are vast, and they all trace back to the elegant dance of quantum fields. But superconductivity is just the beginning. Quantum fields also help us understand topological phases of matter, a relatively new and exciting area of research. Topological phases are states of matter where the global properties of a material are determined by its underlying quantum field structure, rather than just the arrangement of its atoms. These materials exhibit unique properties, such as conducting electricity only on their surfaces while remaining insulating inside. This behavior is robust and resistant to disturbances, making topological materials promising candidates for future technologies like quantum computing. The quantum fields in these systems create patterns and symmetries that are deeply connected to the material's topology, revealing a beautiful interplay between geometry and quantum physics. What makes condensed matter physics so compelling is how it bridges the gap between the abstract and the concrete. Quantum fields, often thought of as the domain of particle physics and cosmology, are just as essential for understanding the materials we interact with every day. Whether it's the zero-resistance flow of electrons in a superconductor or the exotic surface states of a topological insulator, quantum fields provide the language to describe these phenomena with precision and elegance. As we explore these applications, we're reminded of the versatility of quantum field theory. It's not just a tool for understanding the cosmos, it's also a key to unlocking the secrets of the materials that shape our world. Next, we'll delve into another intriguing quantum field, the action field, and its potential connection to one of the universe's greatest mysteries, dark matter. Stay with us as we continue our journey through the quantum realm. Now, let's shift our focus to one of the most intriguing hypothetical quantum fields, the action field. This mysterious field isn't just a theoretical curiosity. It could hold the key to solving two of the biggest puzzles in modern physics, dark matter and the strong CP problem. The action field was first proposed in the late 1970s as a solution to the strong CP problem, a perplexing issue in quantum chromodynamics, or QCD. In simple terms, the strong CP problem asks why the strong nuclear force, which binds quarks together inside protons and neutrons, doesn't seem to care about the direction of time. According to our current understanding, there's no reason why the strong force should be so indifferent to time reversal symmetry, yet experiments show that it is. The action field provides an elegant explanation. It introduces a new quantum field that dynamically adjusts to cancel out any time reversal asymmetry, effectively solving the strong CP problem without requiring any fine-tuning of the laws of physics. But the action field doesn't stop there. It also has the potential to explain dark matter, the invisible substance that makes up about 27% of the universe's mass energy content. If the action field exists, it could give rise to extremely light, weakly interacting particles called actions. These particles would be so light and so numerous that they could permeate the cosmos, forming a kind of cosmic fog that interacts only very weakly with ordinary matter. This makes actions an excellent candidate for dark matter, as their properties align perfectly with what we observe in the universe. Dark matter doesn't emit light, doesn't clump too tightly, and only interacts gravitationally. What's fascinating about actions is that they're not just a theoretical construct. Scientists are actively searching for them using highly sensitive experiments. For example, some experiments use strong magnetic fields to try to convert actions into detectable photons, while others look for subtle changes in the behavior of light as it passes through action-rich regions of space. While no actions have been definitively detected yet, the search is ongoing, and the discovery of these particles would be a monumental breakthrough in physics. The action field represents a beautiful convergence of theoretical elegance and practical significance. It not only solves a long-standing problem in particle physics, but also offers a compelling explanation for one of the universe's greatest mysteries. As we continue to explore the quantum realm, the action field reminds us that even the most abstract ideas can have profound implications for our understanding of reality. Next, we'll explore how quantum fields might influence or even define the nature of time itself, a topic that takes us even deeper into the mysteries of the cosmos. Stay tuned. Now, let's take a step into one of the most mind-bending areas of quantum field theory, how these fields might shape or even define the very fabric of time itself. Time as we experience it feels like a steady, unidirectional flow, but when we zoom into the quantum realm, things get far more mysterious. Quantum fields could hold the key to understanding why time behaves the way it does, and some theories suggest they might even be the foundation of time itself. One fascinating idea is the concept of time crystals. Unlike ordinary crystals which have repeating patterns in space, time crystals exhibit repeating patterns in time. Imagine a structure that oscillates or cycles without any external energy input, almost like a perpetual motion machine, but within the rules of quantum mechanics. These exotic states of matter were first proposed in 2012 and have since been experimentally observed. Time crystals challenge our traditional understanding of time by showing that certain quantum systems can break time symmetry, meaning they don't behave the same way if you reverse the flow of time. This discovery hints that quantum fields might play a role in creating these unusual temporal structures, offering a glimpse into how time itself could emerge from the quantum world. Another intriguing theory is the idea of emergent time. In this framework, time isn't a fundamental feature of the universe, but rather something that arises from the interactions of quantum fields. Think of it like temperature. It's not a property of individual molecules, but emerges from their collective behavior. Similarly, time might be a byproduct of how quantum fields interact and evolve. This perspective aligns with certain approaches in quantum gravity, where space-time itself is seen as an emergent phenomenon rather than a fixed backdrop. If true, it would mean that time, as we know it, is a kind of illusion, a useful way to describe the unfolding of quantum processes rather than an independent entity. These theories open up profound questions about the nature of reality. If quantum fields can influence or even create time, what does that mean for our understanding of cause and effect? Could time itself be subject to quantum fluctuations, just like particles and fields? And if time is emergent, does that imply the possibility of a timeless underlying reality, where events don't unfold in a linear sequence but exist in a more interconnected, timeless state? As we continue to explore these ideas, one thing becomes clear: quantum fields are not just passive players in the universe. They might be the architects of time itself, shaping the very framework in which reality unfolds. Next, we'll dive into the Dirac sea, a concept that connects quantum fields to the mysterious world of antimatter and reveals yet another layer of the quantum universe's complexity. Stay with us as we unravel more of these cosmic puzzles. Now, let's shift our focus to a concept that bridges the quantum world with one of the most intriguing mysteries of the universe: antimatter. At the heart of this connection lies the Dirac sea, a groundbreaking idea proposed by physicist Paul Dirac in the early 20th century. This concept not only revolutionized our understanding of quantum fields, but also introduced the existence of antimatter, a discovery that continues to shape modern physics. The Dirac sea is a theoretical model that describes the vacuum of space as being filled with an infinite sea of negative energy particles. According to Dirac's equations, these particles are normally invisible, but when energy is added to the system, a particle can be excited out of this sea, leaving behind a hole. This hole behaves like a particle with the same mass but opposite charge, what we now call antimatter. For example, if an electron is excited out of the Dirac sea, the hole it leaves behind acts like a positron, the electron's antimatter counterpart. This elegant explanation not only predicted the existence of antimatter, but also provided a framework for understanding how quantum fields give rise to these exotic particles. The discovery of antimatter was a monumental moment in physics. It confirmed Dirac's theory and opened up new avenues for exploring the fundamental nature of reality. Antimatter particles, when they come into contact with their matter counterparts, annihilate each other, releasing a burst of energy. This process is not just a theoretical curiosity. It has practical applications, from medical imaging techniques like PET scans to potential future technologies like antimatter propulsion. But the Dirac sea also raises profound questions. If the vacuum is truly filled with this infinite sea of particles, why don't we observe its effects more directly? The answer lies in the concept of renormalization, a mathematical technique that allows physicists to work with these infinities and make accurate predictions. While the Dirac sea is no longer the primary way physicists describe the vacuum, modern quantum field theory uses more refined tools. It remains a powerful metaphor for understanding the relationship between quantum fields and antimatter. This connection between quantum fields and antimatter also has implications for the early universe. Scientists believe that during the Big Bang, matter and antimatter were created in nearly equal amounts. Yet today, the universe is dominated by matter. Why this asymmetry exists is one of the biggest unanswered questions in physics, and it's a puzzle that quantum field theory is uniquely equipped to explore. By studying the behavior of quantum fields and their interactions, researchers hope to uncover clues about why matter won out over antimatter in the cosmic battle for dominance. As we reflect on the Dirac sea and its role in particle physics, we're reminded of how quantum fields continue to reveal the universe's deepest secrets. From predicting antimatter to shedding light on the origins of the cosmos, these fields are more than just mathematical constructs. They are the threads that weave the fabric of reality. Next, we'll explore how quantum fields might hold the key to understanding the arrow of time, a concept that ties together the past, present, and future in ways that are as mysterious as they are profound. Stay tuned as we dive deeper into the quantum mysteries that shape our universe. Now, let's turn our attention to one of the most fascinating mysteries of the universe, the arrow of time. Why does time move forward and not backward? At first glance, this might seem like a philosophical question, but quantum fields offer a compelling scientific framework to explore it. The arrow of time is deeply connected to the concept of entropy, a measure of disorder in a system, and quantum fields may hold the key to understanding why the universe evolves in one direction. In the early universe, just after the Big Bang, everything was in a state of extremely low entropy, a highly ordered and uniform state. As the universe expanded and cooled, entropy began to increase, leading to the formation of stars, galaxies, and eventually, life as we know it. This increase in entropy is what gives time its direction. But how do quantum fields fit into this picture? Quantum fields are the foundation of all particles and forces, and their behavior influences how entropy evolves over time. For instance, the interactions between quantum fields during the early universe set the stage for the initial low entropy state, creating the conditions for the arrow of time to emerge. One intriguing idea is that quantum fields themselves might encode the arrow of time. In quantum field theory, the vacuum state, the lowest energy state of a field, is not empty but teeming with fluctuations. These fluctuations can influence how particles interact and how systems evolve. Some physicists suggest that the way these quantum fluctuations propagate and interact could be tied to the direction of time. For example, certain quantum processes like particle decay are irreversible and always move forward in time, aligning with the increase in entropy. This suggests that the arrow of time might be an inherent property of quantum fields, woven into the very fabric of reality. Another perspective comes from the study of black holes and their connection to quantum fields. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to the laws of thermodynamics, black holes have entropy, and when matter falls into a black hole, the entropy of the universe increases. This process is governed by quantum fields, which describe how particles and energy behave near the black hole's event horizon. The interplay between quantum fields and black hole thermodynamics provides further evidence that the arrow of time is deeply rooted in the behavior of these fields. But the story doesn't end there. Some theories propose that the arrow of time might not be absolute. In certain exotic scenarios, such as closed time-like curves or regions of spacetime with unusual geometries, time could behave differently. Quantum fields in these regions might exhibit behaviors that challenge our understanding of time's direction. While these ideas are still speculative, they highlight the profound connection between quantum fields and the nature of time. As we explore the relationship between quantum fields and the arrow of time, we're reminded of how deeply interconnected the universe's mysteries are. From the early moments of the Big Bang to the behavior of black holes, quantum fields provide a lens through which we can examine the flow of time itself. Next, we'll venture into the realm of extra dimensions, where quantum fields might exist in ways that stretch our imagination. Stay with us as we continue to unravel the quantum mysteries that shape our understanding of reality. Now, let's stretch our imagination beyond the familiar 3 dimensions of space and 1 of time. What if quantum fields don't just exist in the dimensions we can see and experience, but also in hidden, extra dimensions? This idea might sound like science fiction, but it's a serious area of study in theoretical physics, offering new ways to understand the universe's deepest mysteries. One of the earliest and most influential ideas about extra dimensions comes from Kaluza-Klein theory. Proposed in the early 20th century, this theory suggests that our universe might have more than the 4 dimensions we're used to. In this framework, quantum fields could extend into these extra dimensions, influencing the behavior of particles and forces in ways we can't directly observe. For example, the electromagnetic force and gravity might be unified in higher dimensions, with quantum fields acting as the bridge between them. While Kaluza-Klein theory was initially proposed to unify gravity and electromagnetism, it laid the groundwork for modern theories that explore extra dimensions in even greater depth. Building on this, brain-world scenarios take the idea of extra dimensions to a whole new level. In these models, our entire universe could be a 3-dimensional brain floating in a higher dimensional space. Quantum fields might not only exist on our brain, but also interact with fields in the extra dimensions. This could explain some of the puzzles in modern physics, such as why gravity is so much weaker than the other fundamental forces. If gravity's influence spreads into extra dimensions, it might appear weaker to us confined to our brain. Meanwhile, quantum fields on our brain could be influenced by interactions with fields in the higher dimensional bulk, leading to effects we're only beginning to understand. One of the most intriguing aspects of these theories is how they might connect to string theory. In string theory, particles are not point-like objects but tiny, vibrating strings. These strings exist in a space with 10 or even 11 dimensions, and their vibrations correspond to different particles and forces. Quantum fields in extra dimensions could be the stage on which these strings perform, shaping the properties of particles and the forces between them. For instance, the way a string vibrates in higher dimensions could determine the mass of a particle or the strength of a force, all mediated by quantum fields. But how could we ever detect these extra dimensions if they exist? One possibility is through high-energy experiments, like those conducted at the Large Hadron Collider. If extra dimensions are real, they might leave subtle fingerprints in the behavior of particles, such as unexpected energy losses or the appearance of exotic particles. Quantum fields in these dimensions could also influence phenomena like dark matter or dark energy, offering clues to their existence. While we haven't found definitive evidence yet, the search for extra dimensions continues to push the boundaries of our understanding. As we explore the idea of quantum fields in extra dimensions, we're reminded of how much of the universe remains hidden from our view. These theories challenge us to think beyond the limits of our everyday experience, opening up new possibilities for understanding the cosmos. Next, we'll dive into an even more speculative idea. Could quantum fields be the code of a simulated universe? Stay with us as we continue to unravel the quantum mysteries that shape our reality. Now, let's take a step into one of the most mind-bending ideas in modern physics. What if our universe isn't real but a simulation? This is the core of the simulation hypothesis, and quantum fields might just be the key to understanding how such a simulation could work. Imagine quantum fields as the underlying code of reality, the fundamental programming that dictates how particles behave, forces interact, and even how space and time operate. If our universe is a simulation, quantum fields could be the algorithms running in the background, generating everything we perceive as real. The idea isn't as far-fetched as it might seem. In fact, some physicists and philosophers argue that the precision and mathematical elegance of quantum field theory could hint at a designed universe. Just as a video game relies on code to create a virtual world, quantum fields might be the framework that constructs our reality. For instance, the way particles pop in and out of existence in the quantum vacuum could be likened to pixels rendering on a screen, with quantum fields acting as the software that governs these processes. But how could we ever test such a radical idea? One approach is to look for potential glitches in the simulation. If quantum fields are the code, there might be limits to how finely reality can be rendered, much like how a computer has a finite resolution. Some scientists have proposed that if we could detect these limits perhaps through ultra-precise measurements of particle behavior or the fabric of space-time, we might find evidence that our universe is simulated. Another intriguing possibility is that quantum fields themselves could contain hidden patterns or anomalies, like lines of code that reveal the hand of a programmer. The philosophical implications of this idea are profound. If quantum fields are the code of a simulated universe, it raises questions about the nature of existence, free will, and even the purpose of reality. Are we merely characters in a cosmic simulation, or is there something more to our existence? While these questions might seem more suited to science fiction, they challenge us to rethink our understanding of the universe and our place within it. From a scientific perspective, the simulation hypothesis also pushes us to explore the boundaries of quantum field theory. Could the equations that describe quantum fields be the same equations that a hypothetical simulator uses to run our universe? If so, studying quantum fields might not just help us understand the physical world, it could also give us insights into the nature of reality itself. As we ponder the possibility that quantum fields might be the code of a simulated universe, we're reminded of how much we still have to learn about the cosmos. Whether or not our universe is a simulation, the idea invites us to think creatively and critically about the nature of reality. Next, we'll explore the future of quantum field theory and the unanswered questions that continue to drive scientific discovery. Stay with us as we wrap up this journey through the quantum mysteries that shape our understanding of the universe. As we turn our gaze toward the horizon of scientific discovery, the future of quantum field theory holds both tantalizing possibilities and profound mysteries. This is where the journey of understanding the universe takes its next leap, as researchers around the world push the boundaries of what we know about quantum fields and their role in shaping reality. So, what lies ahead for this groundbreaking field of study? One of the most pressing questions is whether quantum field theory can be unified with gravity. While quantum field theory has been incredibly successful in describing three of the four fundamental forces, electromagnetism, the strong force, and the weak force, it struggles to incorporate gravity in a way that aligns with quantum principles. Theories like string theory and loop quantum gravity aim to bridge this gap, but the path forward remains uncertain. Could a deeper understanding of quantum fields reveal the missing link, or will an entirely new framework be needed to unify the forces of nature? Another exciting frontier is the search for new particles and fields. The standard model of particle physics, built on the foundation of quantum field theory, has been remarkably accurate in predicting the behavior of known particles. Yet, it leaves many questions unanswered, such as the nature of dark matter and dark energy. Could undiscovered quantum fields hold the key to these cosmic mysteries? Experiments like those at the Large Hadron Collider and future observatories are poised to explore these possibilities, potentially uncovering new fields that reshape our understanding of the universe. Advancements in technology are also opening new doors for testing quantum field theory. Ultra-precise measurements of particle interactions, gravitational waves, and even the quantum vacuum itself could reveal subtle effects that were previously undetectable. For instance, experiments probing the Casimir effect or zero-point energy might uncover hidden aspects of quantum fields, shedding light on their deeper structure and behavior. These breakthroughs could not only validate existing theories but also inspire entirely new ones. Theoretical innovations are equally crucial. As physicists refine their mathematical tools and computational methods, they're able to explore quantum fields in ways that were once unimaginable. Concepts like emergent spacetime, where space and time arise from the interactions of quantum fields, are gaining traction. Could spacetime itself be a byproduct of these fields, emerging from their intricate dance? If so, it would fundamentally alter our understanding of the fabric of reality. Beyond the science, the future of quantum field theory also raises philosophical questions. As we delve deeper into the quantum realm, we're forced to confront the nature of existence itself. Are quantum fields the ultimate building blocks of reality, or are they just one layer in a much larger cosmic puzzle? The answers to these questions could redefine not only physics but also our place in the universe. As we look ahead, one thing is certain: the journey of quantum field theory is far from over. With every experiment, every equation, and every new idea, we inch closer to unraveling the mysteries of the cosmos. Whether it's through groundbreaking discoveries or unexpected twists, the future of quantum field theory promises to be as thrilling as the theories we've explored so far. And as we continue to probe the quantum fabric of reality, we're reminded that the universe is always ready to surprise us. As we bring our exploration of the 30 theories about the universe's quantum fields to a close, it's clear that these ideas are more than just abstract concepts. They are the threads that weave together the fabric of reality itself. From the foundational principles of quantum field theory to the speculative edges of the multiverse and beyond, each theory offers a unique lens through which we can glimpse the profound mysteries of existence. Together, they paint a picture of a universe that is far more intricate, interconnected, and awe-inspiring than we could have ever imagined. These theories remind us that the universe is not a static, unchanging entity but a dynamic, ever-evolving tapestry shaped by the interplay of quantum fields. They challenge us to rethink our understanding of space, time, matter, and even consciousness. Whether it's the Higgs field giving particles their mass, the enigmatic nature of dark energy driving cosmic expansion, or the tantalizing possibility of extra dimensions hidden within quantum fields, each discovery pushes the boundaries of what we know and invites us to ask even deeper questions. But the journey doesn't end here. The beauty of science lies in its endless pursuit of knowledge, and quantum field theory is no exception. As we continue to probe the quantum realm, we're not just uncovering the secrets of the universe, we're also uncovering new questions, new mysteries, and new opportunities for discovery. What lies beyond the standard model? Could quantum fields hold the key to unifying all the forces of nature? And what might we learn about our place in the cosmos as we delve deeper into these mysteries? So, as we wrap up this journey through the quantum landscape, I leave you with this thought. The universe is a story still being written, and each of us has a role to play in unraveling its secrets. What do you think lies beyond the horizon of our current understanding? Share your thoughts in the comments below, and let's keep the conversation going. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update as we continue to explore the wonders of the cosmos. Together, let's keep pushing the boundaries of what we know and discover the extraordinary truths